In our quick introduction to capacitors, we mentioned a few formulas, and one very important formula was C is equals to Q over V. This can be rewritten as Q is equals to CV. And I think I stressed the fact that current does not flow through a capacitor. The current I stressed that current flows through it shortly after you apply current after you apply voltage across it. Then shortly immediately after it charges to fullness, it stops conducting current, and that current that flows through it for a short period of time is what we call the displacement current. Displacement current. I should write that down here. Displacement current. Now, we need to be able to estimate the value of the displacement current, and that displacement current can be given. We can get the value of the displacement current by differentiating both sides of this equation with respect to time. Since we know that the Q dt is equals to current I. Current is the rate of change of charge, rate of flow of charge. So if we differentiate both sides, we would have it that since capacitance is constant, we would have it that C is equals to dV dt. So that means that displacement current C is equals to dV dt. So that gives us another formula that we can work with when doing our calculations with our capacitors. This would mean that if we knew the value of the displacement current, we can estimate the value of the voltage V by integrating both sides, and we would have it as the integration of I over C equals Vi dt equals V plus some initial condition. In most cases, this initial voltage is 0, but there are times when it is not 0. So given the current, we can also find the voltage in reverse. So that is another formula we should take note of. Then we might be interested in finding the power dissipated across, or power dissipated by a capacitor, or power delivered to a capacitor. You should recall that power is equals to the product of current and voltage. So we know that the current is C dV dt, and then we can just multiply it by voltage, and then we would have it that P is equals to CV dV dt, and we can integrate both sides. Okay, now this is the we can also write power to be equals to I multiplied by V here. So that would be into 1 over C I dt plus V naught. So those are the two forms our power equations can take. So we can take it one step further by integrating this equation 4, to get the amount of energy stored in the capacitor. So we'll say integral P dt CV dV, and when we integrate power with respect to time, we get work, and when we integrate this, we get half C, oh, this would be the V, sorry, the V, V squared. So we know that energy is equals to half CV square, or work, energy or work, same thing, is equals to half CV square. We should also look at what happens when we connect n capacitors in series with one another. We know that we can replace them with a single capacitance, and the charge across that single capacitance will be V. So we know that all these capacitance must sum up, all the voltages across this capacitance must sum up to be V, and each the charge across each capacitor will be the same, since charges will move from this capacitor to the n-1 capacitor till they reach this capacitor. Then equal number of charges will move to this capacitor. Then equal number of charges will move to this capacitor. Then equal number of charges will move to the power source. So we know that the charges must be the same, and the sum of the voltages across each capacitor must be the same. So we can say that V1, okay, let's call this V naught, is equals to V1 plus V2 plus V3 plus dot 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 Vn, all equals to V naught. And then we can say that Q over CEQ, that's the equivalent, is equals to Q over C1 plus Q over C2 plus Q over C3 plus dot 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 Q over C4. Then we can divide Cn, sorry. Then we can divide through by Q. Then we know that equivalent capacitance for capacitors connected in series is this. Cn, and this is capacitors in series. This would be their equivalent capacitance. Now, if you have to figure out the value of the equivalent capacitance in parallel, we know that the charges among across each capacitor will be different, because this one will gets charged differently, this one will get charged differently, this one will get charged differently, but the voltage across their terminals will be all the same. So we can say that Q, sorry, let's call it QEQ, will be equals to that's the total, the charge on the equivalent capacitor, Q1 plus Q2 plus Q3 plus Qn. And then we can say that CEQ V naught is equals to C1 V naught plus C2 V naught plus C3 V naught plus Cn V naught. So what we just have to do is divide through by V naught, and we would have that the equivalent value of capacitance is C1 plus C2 plus C3 plus Cn. So when you have your capacitors connected in parallel with one another, you want to sum up the capacitances to get the equivalent capacitance. That will be all for today. Don't forget to hit the like button and subscribe. See you next time. Bye.